Hi. In our last module, we left off talking about intermolecular forces. We looked at nonpolar molecules and inert gases, which exist as atoms having dispersion, polar molecules having dipole-dipole, and molecules that exhibit hydrogen bonding, such as water, ammonia, alcohols, and others, have very high boiling points for being molecular because of wonderful hydrogen bonding. Quick review. Dispersion forces are that momentary attraction because of lopsidedness in electron density. Polar molecules over here have a permanent dipole, so we have ourselves positive, negative ends, attraction like magnets. And hydrogen bonding occurs when we have hydrogen, such as in a water molecule, bonded to something very electronegative, such as oxygen or nitrogen or fluorine. What's happening is the attraction between molecules is very, very great because hydrogen's electropositive and it's highly attracted to the negative oxygen on a neighboring molecule. If you want to melt or boil, you need to start breaking these hydrogen bonds, breaking these interactions. They're very quite strong. On the far right, we have an extreme class of compounds, diamond, graphite, quartz, 3 being in this category, called network covalent compounds. And as indicated up on the screen for diamond and graphite, these are networks. We have not discrete molecules, but huge networks. You can think of this as being trillions and trillions of atoms in all directions. And these are held together by covalent bonds. So in the case of diamond here, you would have to break all these tetrahedral sp3 hybridized carbon bonds to go ahead and do a melt or even a boil. It costs a tremendous amount of energy to do that. Now I've left a gap here in the middle, and that's the focus on this module. This is a opening for us for ionic. And I typically write ionic compounds, meaning metal and nonmetal. In this case, I'm going to change the word compound to solid because these all exist as solids where we live. Some of the simple examples are sodium chloride, Na+, metal ion, Cl-, a nonmetal ion. We have very good attraction as though they're point magnets, positive and negative charges. Think of these as being magnets holding each other together. Here's a structure of a sodium chloride. Sodium in yellow, chloride in the darker green. If you want to melt, even boil this, you have to break all of these attractive forces. Positive, negative, positive, negative, positive, negative in 3 dimensions. It takes a tremendous amount of energy. These melt at a minimal of 800 degrees C. We can go ahead and further put these in order within this category based on their magnitude of charge. Sodium chloride have +1, -1 charges. However, compounds such as calcium oxide. Calcium's in group 2 in the periodic table. It's a 2+ charge. Oxygen's in group 17, if you'd like, 6 or 16, excuse me, if you'd like to call it, and that's going to be a -2 charge. These are stronger attractions because we have greater magnitude of charge. Putting these in order, we would put sodium chloride on the left, calcium oxide on the right. Can you think of an ionic compound that has a +3 and a -3? How about aluminum nitride? Aluminum goes +3, nitrogen goes nitride, 3-. That'd be further over to the right. Now we do have a case where we can tell the difference in melting points relative to one another for similar charges based on their size. Let me give you an example of that. For example, sodium chloride +1, -1 charges, sodium fluoride +1, -1 charges. So we need what I usually call a tiebreaker, something that we can go ahead and take a look at and say the charges are the same, but we can pretty much evaluate which one's going to have a higher melting point. Let's take a look at some relative sizes here. For sodium chloride, make a little picture up on the board of a sodium ion and a chloride ion. There we go. And let me take a moment and make a picture of sodium fluoride. Now I'm supposed to make the sodium ions about the same size. Sodium ion, sodium ion. Now the fluoride is going to be considerably smaller than the chloride up above it. Fluorine sits higher up in the periodic table than chlorine. Principal quantum number is going to be less, fewer electrons. And what that means to us is these point charges, sodium plus and fluoride, are going to be closer together. I can demonstrate this by showing you the distance between the center of these ions. If this positive charge is spread throughout the ion, this negative charge spread throughout the ion, then we're looking at the center of these charges, and there's the distance between them. But for the sodium chloride, that distance is going to be farther apart because chloride is significantly larger than fluoride. Now, what does that mean for relative melting point? We would like to, on our chart, put sodium chloride or sodium fluoride, whichever one melts at a higher temperature, over to the right. These over here to the right have higher melting points. Well, it's going to be the sodium, which one do you think? It's going to be the sodium fluoride. The charges are closer together, so the attractive forces are closer together, and it's going to take more energy, more heat, to go ahead and break. Whereas sodium chloride, the charges might be thought of as already being separate compared to sodium fluoride. Distance matters. So we've got sodium chloride, sodium fluoride. The reason, again, the charges are closer together, charges are farther apart, easier.